Okay. Welcome, ladies and gentlemen, to the last session of RemTech Europe, session 16, where it's a training course that will treat improving in situ anaerobic bioremediation performance. The teacher, the trainer, as you prefer, is Robert Borden, from former professor of North Carolina State University and collaborators of EOS Remediation. Bob, the floor is yours. You have two hours. I know that you have also a small break in between. If you may explain briefly to the attendance how will be the structure of the course.
Hello, everyone. Thank you, Marco, for that introduction. My name's Bob Borden. I'm going to be giving this presentation today just for sort of organizational purposes. I'll probably try to take at least one and maybe two breaks partially through the talk, where if you need to get up, walk around, and I'll also be trying to answer some questions right then. So if you have any questions, please type them in on the chat screen. And I guess number one, can you all hear me?
Yep, sounds good.
Perfect. Thank you all so much. I just wanted to make sure that before I kept going. So, little introduction. My name's Bob Borden. I've been working on anaerobic bioremediation for now maybe 20 years. I'm a principal engineer with EOS Remediation and a emeritus professor of civil and environmental engineering at North Carolina State. Worked on a lot of different processes, minor notch attenuation, enhanced bioremediation for a wide variety of compounds. It's fairly late on a Friday afternoon for some of you, so I hope you have your little glass of wine there, and I'll try not to keep things interesting. So first, why do anaerobic bioremediation? Well, I think the simple answer is it works. What I've got shown up on the screen is some monitoring data collected in a project by Travis McGuire for ESTCP. And what they did is they went out to a large number, they basically collected published technical reports, monitoring reports for a large number of sites. And they essentially plotted up, you can see on the right, a graph of the concentration before treatment on the x-axis and the average site concentration after treatment on the y-axis. And what's shown here is just for bioremediation, but they also looked at other technologies. This heavy black 45-degree angle line, that would be what would happen if there was no treatment. The concentration after treatment would be the same as the concentration before. And as you go down this, when you see, well, this dashed line here is 1 order of magnitude reduction, that would be a 90% reduction. 2 orders of magnitude would be 99%. 3 orders of magnitude would be 99.9%. And what you can see here is that, there are a lot of bioremediation projects they were able to evaluate. Most of them were, I'm going to say in the 0.1 to 10, maybe 50 milligram per liter range of parent compound. And they've got, well, they even have a few where concentration went up. Well, obviously that's not what we're hoping for, but if you've got 117 sites, there are going to be a few that just don't work right. But you can see the majority here, they got, 1, 2 orders of magnitude. And actually some sites here down on the x-axis, they got essentially complete removal. They started here at maybe a milligram per liter, and by the end of the project, it was below detection. So there's some sites that do very, very well. Unfortunately, there's some sites that don't do as well. And that's really the focus of this talk, is trying to help you all optimize design so that, well, we can have more data points down here on the x-axis and fewer up here. What's the second reason why people like to use anaerobic bioremediation? Well, the simple answer is that there's a lot of other technologies that actually work fairly well initially. You go out, you do the treatment, and they get a big reduction in concentration. But then they often see rebound, where the concentrations will rise back up again after a year or two. I think one of the very attractive things about anaerobic bio is that rebound seems to be significantly less. What I've got shown here, again, Travis collected data from a number of different sites with, I believe, at least 5 years of monitoring data. Average was probably more like 8 or 9. And what they did is they looked at the concentration. If you look at these, the light colored or the light shaded bar is the concentration at the end of the first year of treatment. And then the heavier dark line is the concentration at the last monitoring point. And what you see there is that, well, for about, I don't know, a third of the sites, concentration treatment actually improved over time. They finished treatment and they're at this level, and then they went back 5 or 10 years later and the concentration was actually lower still. So there's no rebound. There's another, maybe that's not a third, maybe that's 20% of the sites where there was really no change. And there was a third where there was some rebound, where treatment was better after 1 year than at the end of the project, at the end of the monitoring period. But, the rebound wasn't necessarily horrible. They still got some treatment. It just wasn't quite as good as they initially observed. And there's a lot of reasons, we can talk about that later, why this happened, but it does seem to be fairly common that anaerobic bio tends to have less issues with rebound than some other technologies. Okay, so give you a little overview of the way this course is going to go. I'm going to do an overview of the general technology, contaminants can be treated. We'll talk a little about substrate. My particular expertise is on using emulsified vegetable oil, or EVO. And so I'll go through that. I'll explain some about the particular details of EVO transport. We'll go through a case study and I'll show you a simple design tool. Okay, so what is anaerobic bioremediation? Essentially what people do is they'll go out, they have a contaminated site, they'll install a series of wells or injection points, and they'll inject an organic substrate. That organic substrate will consume back around electron acceptors like oxygen, nitrate, iron, and sulfate. And any substrate left over at that point will be fermented to hydrogen or acetate. They're naturally occurring bacteria that can use a hydrogen acetate as an electron donor to reduce the contaminants. That's it. Okay, what contaminants can you treat? I think it's very well known that you can treat chlorinated ethenes. That's probably the single biggest sort of use of this technology. I think it's like PC and TCE. Sorry about that. Got a phone call, but we're back on track. You can also treat chlorinated ethanes, methanes, explosives like TNT and RDX, nitrate, perchlorate, chromate, certain radionuclides, as well as acid mining drainage. Okay, what kind of electron donors do people use? Well, I'm going to say there's really two major classes that are in real common use. One is soluble substrates, things like fatty acids, sugars, alcohols. They work very well. They're easy to inject and distribute. One of the nice things about it, they stimulate very rapid biodegradation, which is good for stimulating degradation the challenge is that they get consumed very rapidly. And so you typically have to go back and re-inject anywhere from maybe once every 2 weeks to every 2 months, maybe. But it's pretty frequent, and so it generates a fair amount of operating maintenance costs over the course of the project. The other issue is that since you're injecting these substrates fairly frequently, you tend to generate a lot of biomass in the injection wells. That'll plug up the well over time. You can clean those out, but it does require some labor, some work to do that. The other sort of alternative that I'm going to spend most of today talking about is use of emulsified vegetable oils. These are basically oil droplets prepared with some kind of surfactant, make little tiny droplets. They get transported through the aquifer. We would inject them. They'd attach to the soil particles. Over time, those particles will biodegrade, releasing carbon. And the nice thing about it is, and I'll explain later why, but the oil degrades fairly slowly in the subsurface. So a single injection might last anywhere from 3 to 5 years. We actually have sites that last longer, but we also definitely have sites where it's less than 3 years. Real high velocity aquifers, it might only be 1 or 2 years. The key thing that I'm going to keep emphasizing today is that, excuse me a second, take a drink of water. So back, sorry. I need to keep reminding myself to take a sip periodically. I get going. So anyway, the key thing to get good treatment is you have to distribute the oil effectively throughout the formation. And to do that, you simply have to inject enough oil to saturate the sites. Now, I've been talking about soluble substrates and emulsified oils as separate things. Actually, what we see much more lately is that many people are using essentially a mixture of soluble substrates, oil, and often there's nutrients, nitrogen, phosphorus, B12 added to it. And this is really this third joint category, I'm going to say, is really the focus of today's talk. Okay, so how does this all work? Well, I think something over 20 years ago, we first started on this. Had a grad student, we worked on a site, we constructed, we didn't do it, he did all the work, I just get the credit for it. But we obtained aquifer material, we constructed microcosms, amended it with 500 milligrams per liter of soybean oil. And you can see already the groundwater in the soil used it. There was a little bit of PCE, a fair amount of DCE in the microcosm. It took about a month for things to wake up, but then, pretty quickly we started getting degradation of the DCE and TCE started producing a little bit of vinyl chloride, but then the vinyl chloride degraded and we produced a lot of ethene. So we were very happy about this. Grad student was happy. He packed up, graduated, went away. Unfortunately, like many grad students, didn't necessarily clean up everything. And I think probably a year later, we discovered these bottles in an incubator somewhere. So we said, well, what happened? So we respiked it. We added about 20 milligrams per liter of PCE. It degraded, then we added some more. Then we added some more. Then we added some more. Well, what I'm showing you here is actually the results after the 5th respike with 20 milligrams per liter PCE. And this was done, well, I guess we respiked with additional PCE on day 835, 835 days after they were originally set up. Now, and we added 20 milligrams per liter of PCE. That's equivalent to about 120 micrograms, micromolar of PCE. if you do that conversion. And that's that first symbol, that red dot right there. Well, that doesn't make sense. That red dot says we've got about 13 micromolar, but I just said we put 120 in. Well, that first point is the day after we respike. And so in that 24 hours, about 90% of the PCE somehow disappeared. Well, we now understand that essentially what happened is the PCE sorbed to the soybean oil in the bottle. So it was unavailable. So when we measured the aqueous concentration, it wasn't there. Well, over the next 2 months, as the aqueous PC concentration went down, some of that PC desorbed, it got degraded, then more desorbed, then it got degraded, and more desorbed, it got degraded. And then over 2 months here, we can see that essentially all the PCE went away, all the TCE went away, DC got produced and went away, vinyl chloride got produced and went away. And at the end of that 2 month period, we recovered, well, not 100%, but I don't know, 80 or 90% of the added material as ethene. So we got pretty close to a mass balance. And while initially the PCE did appear to sorb the soil or the contaminant, eventually it all degraded. So, you know, that was a very, very nice result, at least at the laboratory. And so then we wanted to try to figure out how to get this to work in the field. Before I go on that, I want to spend a little bit of time digging into some of the details. I just showed you how PCE gets degraded to TC to DCE, but let's talk a little bit more about that. So this is that pathway. I'm sure you've all seen it before, where PCE can get reduced to TCE, and that's done by, we have an external electron donor that provides electrons. Microorganisms use that to, they'll basically remove a chlorine and replace it with a hydrogen, and in the process, release HCl. That's hydrochloric acid. And then another of the same organ will reduce that to TCE or to DCE, and then DC to vinyl chloride, and vinyl chloride to ethene. Now, this really is one continuous process, but in some ways it's actually almost two separate processes. We've got an initial step here, PCE to TCE to DCE. That step can be carried out by a wide variety of organisms. So Dihalobacter, the Sulphomonas, Geobacter, a number of different organisms. These organisms are fairly common. They grow rapidly. They can use either hydrogen or acetate. Well, I don't say all of them, but certainly some of these organisms can use acetate as electron donor. They can fix nitrogen to make ammonia. A number of the organisms can actually produce B12 for their own use. And they tend to be less sensitive to pH. So this process here is a pretty robust process that generally goes very rapidly, at least our experience. When we do a project, we rarely have problems getting from PC to TC to DCE. The bigger challenge occurs in this second step, trying to convert DCE to ethene. As far as we know, or at least currently, the dominant organisms that believed to carry this process is the Halicoides bacardii. The good thing about this organism, it can convert DCE to non-toxic ethene. Sort of the not so good thing about it is that it grows fairly slowly. It cannot use acetate. It must have hydrogen as electron donor. It requires an external ammonia source, and it requires an external B12 source, and tends to be really quite sensitive to pH. So you need a pH above 6.3 for this process to go effectively. So, you know, we see both of these processes occurring. But oftentimes what you'll find is the second step is slower than the first step. And we need to really work to make sure that this second step is optimized and is going as quickly as possible to get good cleanup rates. Okay, so how do we solve that first problem? Well, what happens if there's no bugs? Well, our simple answer is we recommend people bioevaluate. Typically what we'll do is recommend that you go out, take soil or groundwater samples, analyze them by qPCR, see if there are appropriate organisms there. If they're not, add them. It does cost, you know, there is a significant cost of buying the organisms, and there's labor to do the injection. So there is a downside to bioremediation, but the reality is that waiting is expensive. If it turns out you don't have the right organisms, you have to go out, you have to re-eject, you keep monitoring. That all costs time and money. And so our experience has really been that if you don't have, you know, reasonably good counts ahead of time, we'll often just go ahead and bioaugment it. It doesn't cost that much, and in the end, it's worthwhile. Okay, another item, nitrogen and phosphorus. Essentially all bacteria require nitrogen and phosphorus for growth. Many years ago, there was this ratio that was developed, the Redfield ratio, that basically describes the ratio of carbon to nitrogen, phosphorus, and biomass. And sort of on average, this does vary, but on average, that ratio is 106 to 16 to 1. And so if you're going to grow bacteria, and that's part of what we're trying to do here, is in addition to provided carbon, you also need to add nitrogen. But you need to add it in the ratio where where actually biomass grows. In anaerobic bioremediation, typically about 90% of the carbon ends up going to methane and carbon dioxide. So what we recommend is trying to supply nutrients, carbon to ammonia, or to nitrogen and phosphorus, more like 1,000 or 1,060 to 16 to 1, since most of the carbon will go to other pathways and not be used for cell growth. These organisms need B12. Dihalococoides McCartyi actually requires B12 for growth. You can see in the graph on the right. These are 3 different strains of Dihalococoides that were tested. You can see they all grew much, much more rapidly and effectively with B12 added. I will tell you, you do not need to add B12 at every site. You do not need to add ammonium phosphorus at every site. But where you need it, it really helps. My personal experience is it just seems like we run into a B12 limitation more often at high sulfite sites. I'm not completely sure why. I've often, you know, it might be due to shifts in population of organisms. Sort of my pet theory was always that actually these sites were making, since there's a lot of sulfate present, we're making a fair amount of hydrogen sulfide. Cobalt, a key element in the formation of B12, is incredibly insoluble in the presence of sulfide. So there's a chance that actually we're precipitating cobalt, and that's leading to the B12 limitation. Regardless, don't know exactly why, but we clearly do know that added B12 is helpful. Another point, pH. We have learned over the past few years that, well, certain steps in this process are extremely pH sensitive. What I've shown here is my results from a study of a bioagmentation culture by Ashley Eady from Clemson University. And what you can see here is, well, at pH 7, they got very rapid conversion of TCE. at pH 6.5, 6, and even 5.5, they got pretty good conversion of PCE. Yeah, at 5.5 it was slower, but they still got, you know, good degradation of TCE and production of DCE. But now we go to the next step when you look at vinyl chloride conversion to ethene. At 7, they got very good rates. At 6.5, well, there was a lag and it still occurred. At 6, it was greatly reduced. And at 5.5, it was completely inhibited. So don't necessarily completely understand why, but it's clear that this final step of PCE, of vinyl chloride to ethene conversion is much more pH sensitive, and we need to be aware of that. There is some interest in specialized bioaugmentation cultures that are more pH tolerant. This was a paper that came out of, I guess about a year ago, out of Elizabeth Edwards' lab. And what they did is they've been working, trying to enrich for a Halicocoides culture that was effective at lower pH. And they actually had some success. They were able to get it to grow at lower pHs and degrade things. Later on in the project, what they did is they took that culture and they actually, but it was a cell, they broke up the cells so it released the internal enzymes, and then they did their test with just the cell-free extracts. And that's what's shown on the right here. And you can see here that this is vinyl chloride production from DCE. And they've got very rapid, at pH 7, very, very rapid conversion of DC to vinyl chloride. At pH 6, almost an order of magnitude lower rates. At 5.5, lower still, and at 5.0, very, very low. So while, you know, they were able to make this culture a little less sensitive to pH, and I actually think there may be some benefit to using these cultures. In the end, it was still sensitive to pH, just not quite as much so. And based on this, I would still say that it would be good, if at all possible, to maintain pH above 6.3 to get really good degradation rates and efficient treatment. Okay, some design alternatives. Okay, so I'm gonna, as I said, I'm talking mostly about using emulsified vegetable oil. And there's thousands of different permutations you can use this process as, but really it often kind of breaks down to two big alternatives. One is barriers, and in a barrier design, we'd go downgraded the source area, and we did install a series of wells in roughly a barrier, cutting off the plume. And then we inject the emulsified soybean oil or emulsified vegetable oil into these wells. And we formed an oil treated zone that now the plume had to migrate through. And as it migrates through, it gets treated, you get clean groundwater on the downradiant side. Advantage of this, it tends to actually be a very efficient process because you bring the contaminant to the oil. And so it's very easy to get really very good contact. Another advantage, you don't have to precisely define the source area, and so capital and operating costs are generally lower, fewer injection points. Overall, it's pretty easy and effective technology. The disadvantage is it doesn't actually eliminate the source. You still have this source up here that's going to be bleeding out some dissolved contaminant for years or decades, and you haven't destroyed that source. So a lot of times people really want to know, I want to attack the source. So this figure at the bottom is sort of my imagination of what a source area might be. And if we're going to do source area treatment, we would basically cover that area with injector wells, and we essentially try to flood the entire thing. In that way, we're going to bring the oil in as close contact as possible, the contaminant, to destroy it. Now, the reality is, if you sort of zoomed in here, what you probably see is, at most sites, it seems that there's there's some heterogeneity. There might be some clay zones and some sandy zones, and then another clay zone. Well, it's very difficult to transport the oil droplets into clay zones. It's not so much they won't fit, we can do that. It's just the oil droplets are carried by water. Well, if water doesn't effectively flow through clay, and so it's really hard to transport the oil with it. So really what we end up doing is we tend to treat the sandy zones directly adjoining the clay. And then over time, as you know, contaminants, TCE, diffuse out of the clay into the sand, they'll get degraded. So we've almost, in a way, we built a barrier here, but it's kind of a internal barrier. As it leaks out, as the TCE leaks out, it comes in contact with substrate and degrades. Okay, let's dig a little bit more into the details of this process. What I've got up here is a picture of a soybean oil molecule. The soybean is basically a glycerol at the center with 3 long chain fatty acids attached. Bacteria can't eat this directly. So what they'll do is they'll hydrolyze the glycerol fatty acid linkages, releasing the fatty acid. The glycerol is soluble, easy to degrade, so that gets fermented very, very quickly. And then the soybean oil, well, it goes through a process called beta oxidation. A typical soybean oil would be linoleic acid. That's a C18 fatty acid. And what the bacteria will do is they'll take the C18 and they'll basically clip off a 2-carbon segment. That 2-carbon segment is essentially acetic acid. And so using C18 fatty acid, they'll produce C16 fatty acid, some acetic acid, and molecular hydrogen. Then they'll take the C16, they'll remove 2 carbons, make C14 and another hydrogen, and they keep doing that process progressively, whittling that down. So the fatty acid will eventually release, well, a lot of acetic acid or acetate and a lot of hydrogen. One of the big advantages of vegetable oil is it's a more reduced compound. So you tend to generate actually significantly more hydrogen than other substrates. And so this actually works really pretty well. That's the good news. The sort of maybe not so good news is that, well, these long chain fatty acids, I keep talking about linoleic acid. Well, if you take a long chain fatty acid and you add sodium hydroxide to it, you get soap. You know, that's the way, I don't know, your grandmother or your great-great-grandmother used to make soap, where they'd have a big, you know, vat of fat and they cook it with caustic soda and they make bar soap. Well, bar soap is actually, sodium soap is actually fairly soluble and mobile. The problem occurs is when there's calcium or magnesium or iron or in the formation. These materials are divalent cations, so they've got a +2 on them. And essentially what happens is the long chain fatty acid co-precipitates with the calcium and it makes soap scum. Soap scum it's got a pretty low solubility. Bacteria can really only use the soluble fraction. So when it precipitates out as the soap scum, it's much less bioavailable, so it doesn't ferment as fast. That's sort of a good and a bad point. It slows the fermentation rate, so you're not producing acetate and hydrogen quite as quickly, but it also makes it last longer. That's exactly why soybean oil or vegetable oils you can inject and it'll last 3 or 5 years. Because in any moment in time, most of the oil is actually precipitated and isn't really readily available. Okay, why do we really care about that? Okay, so as I said before, This slow fermentation releases both acetate and hydrogen. Acetate is, I mean, it's an okay substrate, but it's not a great substrate for dechlorination. It's got a relatively low energy yield, so it isn't consumed that quickly. And since it's not consumed quickly, it can migrate a pretty good distance. When you monitor TOC in groundwater, often what you're really measuring is acetate. Now, the other thing that gets produced in this fermentation is hydrogen. Hydrogen is what the best substrate of all, because that, or electron donor of all, because that will stimulate conversion of DC to vinyl chloride to ethene. Remember, to do DC degradation, we need hydrogen. Acetate won't work. Well, hydrogen is such a good electron donor that it's also consumed really, really rapidly. It can be used not only for degradation of the chlorinated compounds or the target contaminants, but it's also a great electron donor for iron reduction, sulfate reduction, methanogenesis. And as a result, hydrogen does not migrate really any significant distance. It gets produced at a location and it will get consumed pretty quickly. So to get effective degradation, we need hydrogen. To get hydrogen, we need a fermentable carbon source that releases hydrogen. That could be oil itself, or it could be longer, fatty acids like propionate, butyrate, valerate. So there's a number of fatty acids that can produce hydrogen. Unfortunately, acetate will not produce hydrogen. So that's a really critical thing here that I think you need to understand is we need to get a fermentable carbon source that releases in hydrogen in close contact with a contaminant. And yeah, I think that's it. Let me just take a break here for a second. Let's see can somebody take a look and see if there's any, trying to see if chat, okay. Question, is the Halichocoides McCarty only convert DC to ethane, or does it convert? Yeah, well, different strain. Okay, so let me ask a question. There was a question, can the Halichocoides McCarty convert DC down to ethane, or does it convert PC/TC all the way to ethane? Well, the answer to that is it can do both. Some cultures will, the Halichocoides will convert PC to TCE to vinyl chloride to ethene. There's some others that may only use DCE. Typically, all the bioaugmentation cultures you would purchase would actually be a mixture of organisms. Some organisms that will be very good at converting TCE to DCE, maybe a different type of organism that converts DCE to vinyl chloride, and maybe a different one that converts vinyl chloride to ethene. So the cultures you typically buy will be able to complete the process. Question for later, how do you normally test if ammonium phosphate or B12 is needed at a site? Okay, so I had a question, how do you know if you need ammonia or phosphorus or B12? Okay, I know I'm not supposed to say this, but I have no idea. Well, I really have no idea until it's too late. I'll show you a case study later on today where we didn't add B12 and we didn't add excess ammonium phosphate, and then I wasn't getting good dechlorination. We did microcosm studies and I found that we were nutrient limited. The solution we now use is, I pretty much added it every site because the few times when I haven't added it, it hasn't worked. And that's what I got, sorry. Any other questions? Well, do we need a bio break or anything else? Okay, well, here, let me take a little sip. What time is it? It's 11:43, so I guess we're about, well, Eastern time. I guess it's 5:43 for those of you in Italy. Well, okay, I guess I'll keep going on. Okay, I've emphasized how important it is to get good distribution in the oil. Now I want to kind of take a step back and say, well, okay, great, you convinced me that it's important. How do I do it? Well, first step in that, you need to understand a little bit about how these little oil droplets actually get transported. And what I'm going to give you is sort of our conceptual model of how this occurs. But it's that conceptual model is really backed up by a lot of laboratory and field data. So step one, well, number one, I'm going to click this video and then I'm going to sort of talk through it. As we imagine transport, okay, first of all, the oil droplets that most people use, we use, are typically on the order of about 1 micron. Most sediment pores in aquifers are anywhere from 30 to 100 to 200 or 300 microns. So the oil droplets are much, much smaller than the pathways in the aquifer, or the major pathways in the aquifer. And so physical screening is not an issue. The oil droplets can easily pass. Now, what the issue is, well, the big controlling factor is the droplets we make and a lot of things are negatively charged. So each of these little droplets has a negative charge on it. Sediment surfaces, people will say they're negatively charged, but actually there's a mixture of charge sites. Some are positively charged, some are negatively charged. As the oil droplets float by, if they encounter a negatively charged surface, they get repelled and they move on. If they encounter a positively charged surface, they'll stick to it. But there's only a certain number of positively charged sites. The video right now shows that basically we've now saturated all those positively charged sites with oil droplets. Now they got an oil droplet stuck to it, no more oil can stick. And from this point on, the oil is going to transport very, very readily. So the key thing here is that, okay, step one, the oil droplet must bump into a sediment particle. It's got to stick. For it to stick, there has to be sort of an open spot available. What we found is that, well, let me move on to the next slide. I'll explain a little bit better. What we found is that there's a term what we're going to call maximum oil retention. That's essentially the capacity of soil to hold oil droplets as when it's fully saturated. Typically what you find is that silts and clays have more surface area, they have more charged sites, so they can hold more oil. It also depends on one of the surfactants. Non-ionics tend to have lower retention, ionics have higher retention. So what I've got shown on the right there is a photograph of an oil retention test. It's basically a column test. We'll get aquifer material, we'll pack it into a column, and then we'll pump almost like vegetable oil through the column with a pump. You can actually see the upper part of this column is sort of darker brown while the lower part is white. That's the EVO emulsion, EOS Pro, sort of moving up through that column gradually. Our procedures will flush 3 full pour volumes of emulsion through it to fully saturate it. And then we'll flush water through to wash out any particles that are not attached. And then we measure the amount of oil retained. What we find is that this amount, once it's fully saturated, increases with clay content. The other thing we've discovered recently is it increases depending on the water chemistry. Here are some results of measured oil retention. Most of these tests were done by microbial insights. And you can see here, this is a cumulative frequency distribution. So on the bottom, we've got maximum oil retention. The lowest retention we ever measured was 0.0001 grams per gram. The highest was, well, not 0.1, but maybe 0.08 or something like that. And so here, the median, it looks like the median oil retention, the 50% point, is maybe 0.008 grams per gram, something like that. So a pretty broad range. Early on, when we were working on this, seemed like all our data was in this region, but over time we found a few sites with really, really much higher oil retention. And the key thing is, that as I described before, if you want to spread oil out, you have to sort of fill up the sites near your injection well first before it will migrate farther. Okay. As part of this process, we've done a lot of experimental work. We've done column tests to look at transport. What I'm going to show you here today is results from some larger scale sand tank experiments. The picture on the right is a photograph of a radial flow sandbox. The box is about approximately 1 meter wide by 1 meter deep by 1 meter tall. In the front left-hand, well, let me go back. In the front left-hand corner of this photograph, you can't see it, but there's a 1-inch PVC injection well buried in that sand. And on the right side and in the back, we've got a constant head boundary maintained. So if we have this injection well here, we inject here, most light oil is going to flow out radially from that well towards these boundaries, and we're going to be able to see it migrate across. Now, in the experiment that I'm going to show you, we packed this tank with actually a higher permeability sand in the middle, a little lower on the top, and lowest of all on the bottom. And here's a photograph of, I don't know, maybe halfway through the injection. And you can see here, the normal color of the sand was sort of a darker brown or tan. Here in the front left corner, you can see it sort of look kind of like whitewashed, kind of milky. That's the EVO. It's migrating through the tank. You can see it goes more rapidly through certain layers than others and kind of streaks through there. And then, so this is about halfway through the injection. This photograph is after we complete the injection and we flushed 3 pour volumes of clean water through the tank. And you can see even after we flushed all that clean water through the tank, there's still a fair amount of oil coated to the sediment surfaces. And we sort of, well, we kind of painted the entire aquifer with this sort of like film of vegetable oil. And that's going to provide our carbon source for biodegradation. Like all good college professors, I had to have some partial differential equations. They're on the lower left-hand side. Don't worry, I'm not going to make you do anything with those. We essentially took a standard colloid transport model used to, it's actually commonly used to simulate transport of bacterial particles, of bacteria through aquifers. We ran column tests with these 3 different sediments I described, measured the oil retention parameters in the column test, stuck them in the model and made a prediction of how oil would transport in the sandbox. That prediction is the line on the right. The dots are actually the measured values and little mini monitor wells at different distances. And as you can see, well, I felt like the curves matched pretty well, actually, where, you know, we got breakthrough right about when we intended, the size of the peak changed. Now, I will tell you there was one point here, down here, where the model really did a pretty much terrible job of predicting. But other than that, you know, we sort of matched pretty well where the observed distribution matched, the predicted distribution matched the observed. So we felt like, well, we actually have a pretty good understanding of the physics or the fluid mechanics of oil droplet transport in the subsurface. Now that we have that understanding, we're going to use this model to try to look at it at different injection approaches and try to find the best injection approach. So what I've got here is sort of our imagination of what the upper picture is of the permeability distribution in an aquifer. You're looking at a vertical profile. The aquifer is about 3 meters thick vertically by, I guess that's probably about 30 meters horizontally. And I've got 2 injection wells in the middle. Dark red zones are higher permeability zones. White is lower permeability. And we've got a scale bar here on the left. So white is, I think that's, I don't know what the unit of that white is. I'm going to say that might be meters per day in the white. So pretty large permeability contrasts. The lower figure is simulation results for, well, a specific amount of oil and water we injected. And I'll explain what this SFB and SFF means in a moment. But let me just take a moment and sort of talk about what you're seeing here. So we inject the oil and then chase water. You can see here near the injection well on the left, pretty much all the area near the injection well is treated. But we've got these fingers that extend out. Well, you can see here in between the 2 injection wells, there's this one zone where oil treated aquifer from materials spreads it all the way across. Not surprisingly, if you go up to the top, that zone where we got really good distribution of oil happens to be a high. The water moved, the oil went. Down here, it's white, and this is essentially untreated. And if you look up here, well, that's the low K zone. Particularly dramatic here over on the right. We've got this big white area here that's untreated. Well, that's a low K zone. And that's as, you know, and it's not because the oil droplets can't move there. This model actually doesn't know the exact droplet size. What it knows is where the water goes. All the water goes to the high K, so all the oil goes to the high K. Now, the other thing I want to point out is really the very sharp contrast we see. The way oil droplet transport works is that oil won't migrate far until you almost fill up all the sites. So we see if the dark red, that's completely saturated. The white is completely unsaturated, and a pretty sharp interval in between. Now, what we really want to do, as I said, is really important to bring the oil in close contact with the contaminant. If we're here in the white zone, well, upgrading of that, there's going to be oil. That oil is going to produce hydrogen and acetate. Most of the hydrogen will get consumed pretty quickly right here and right here. We'll probably actually have very good acetate concentrations. We'll probably get very good treatment of PCE and TCE, and we'll make cis. So I would expect if you actually did this distribution, you'd find essentially PC and TCE are non-detect throughout. We're only going to get good conversion of DCE to vinyl chloride all the way to ethene in the zones where we've actually got oil close by. And so what we want to do is, realistically, is spread the oil out as far and as uniformly as we can so we bring oil in close contact with the contaminants. It doesn't have to be perfect, but the better we can get, the better treatment, the more rapid cleanup of the site we're going to get. So what we did is we went back and we ran a whole bunch of simulations, trying to figure out, well, okay, the objective is uniform treatment. How do we get there? And what we found is that really the two key factors are the amount of oil you inject and the amount of water you inject. We represent the amount of oil as I talked before about a maximum oil retention. Well, I think you can see that for the aquifer, if it's 3 meters high by 30 meters long, that's got a certain mass. If we know the maximum oil retention per gram, you can calculate the maximum oil retention for that volume of aquifer. The mass scaling factor is the ratio of the amount of oil we inject to the maximum that could be retained. So if you got a value of 1 here, you injected enough oil to saturate 100% of the sites in the treatment zone. The volume scaling factor is essentially the pore volumes of water you inject. So again, if the porosity of that zone times its volume is say 10 cubic meters, and we inject 10 cubic meters of fluid, then we have a volume scaling factor of 0.1. The vertical axis here is the contact efficiency. So if I inject 1 pore volume of water and 100% of the oil retention, the lines intersect there, and that would predict that I get a contact efficiency of about, I don't know, maybe that's 90%, something like that. So at least in barrier situations, we can get very good flow contact efficiency. Now the problem is injecting all that water and all that soil and all that oil costs a lot of money. I don't want to spend all that much money. Well, if I cut the oil back to say half the maximum retention, and I inject 0.5 pore volumes, well, that will intersect here, and that looks like maybe I've got 80% contact efficiency. So I reduced the oil amount I inject by 50%, the water by 50%, and my contact efficiency has dropped from 90% to 80%. I don't know whether that's really, okay or not. That's really up for the designer to decide what contact efficiency they want. We clearly know more is better, but you can also see there's clearly sort of a law of diminishing return here. Once you get above about 75 or 80%, it's fairly easy to get to this point here. You have to spend significantly more money to get to this 90 and 95%. Okay, how are some ways we can improve contact efficiency? Some other ways other than just amount of oil. Well, one of the things we've seen in a number of projects really early on was that it's a lot of times if you inject all the wells at once, you can create stagnation zones. And I'm going to point that up at the top here. So imagine I wanted to install a permeable reactive barrier. I've got a series of injection wells here, and I inject all the wells simultaneously. Well, if I inject wells C and B at the same time, water with oil is going to flow radially out from the injection well to the left, and it's also going to flow from B out to the right. When this streamline and this streamline intersect, there's going to be a stagnation zone. Stagnation zone, the water velocity is 0, which means oil is not transported there. So instead, since the water can't go to the left and right, it goes up and down. And you get sort of these elongated blobs where we've got better spread vertically perpendicular to the barrier than along the side of the barrier. Well, one way to fix that or solve that problem is don't inject all the wells at the same time. Instead, inject wells A, C, and E at one time. We do that, streamlines will flow out here, and the stagnation zone will form right over where well B is. You do that on the first day. The next day, you come back out, and then you inject B and D. B and D are exactly centered over the old stagnation zone. So we're going to get great contact efficiency there. The graph at the bottom shows sort of the benefit. If you're only injecting, you know, 2/10 of a pore volume, really it doesn't matter that much. Your contact efficiency is low enough that there isn't that much benefit. But as we try to get higher and higher contact efficiencies using this alternating injection approach, works very well in that, you know, for really no additional cost, you can get yourself another, well, you know, 10% contact efficiency at the highest. And we really think that that's worthwhile. It should be. One last thing I want to mention, we really do encourage people after, you know, to do this in phases. And typically what we'll inject the water EVO first, or at least a more concentrated EVO solution first, and then we flush with water to clean out that well. And I'll explain that in a minute. Okay, so what I want to do is I want to go through a little case study. This was actually, again, it's like 15 years ago, I think we did this project or more. It was a former, the groundwater at this site is contaminated with perchlorate, ClO4, and trichloroethane. Also has a little bit of TCE, but really the primary chlorinated solvent is TCA. We wanted to test a biobarrier, and this was one of the first sites we worked on. And the site owner was, well, they were a little cautious. They weren't completely sure this was going to work perfectly. And so what they did is they had us do this pilot test, upgrade it, well, sort of in the middle of an existing pump and treat system. About 10 years before we got started at the site, or maybe it was 15, but sometime before we got started, they put in an interceptor trench down here where they extracted groundwater. They pumped it, upgraded it to an infiltrate. They pumped it, upgraded it, ran it through an air stripper to remove the chlorinated solvents. And then they re-infiltrated the groundwater in the infiltration gallery. That generated a flow field where groundwater is flowing from here to here. We went fairly short distance, upgraded an interceptor trench, and we put our biobarrier here. That biobarrier is downgraded of the source here, which is number 34. That was where the original source was. Okay, this is what the barrier layout looked like. The red dots here are injection wells. Blue symbols are monitor wells. We had 3 monitor wells upgrading the barrier, 5 monitor wells downgraded the barrier. Geology, it's water table is about 3 meters below grade. We've got about a 3 meter thick saturated silty clay. There's a silty clay about 6 meters. So it's got about 3 meter saturated zone. When we got started on this project, we were essentially basing all our work on the design in the pump and treat system. They had reported a hydraulic connectivity of 0.3 meters per day. So, well, that's what we assumed it was. And so we designed this barrier, placing our injection wells just 1.5 meters apart. Well, it turns out that that K value was wrong. And a better estimate of K for the aquifer was probably 7 to 16 meters per day. We found that out after we put all these wells in and we did slug tests and discovered the permeability was quite a bit higher. The other thing that's a little unusual about this site is that since we're sort of in the middle of a pump and treat system, the hydraulic gradient is really pretty high. And so we had groundwater velocities in the range of 100 to 250 meters per year when the pump and treat system was operating. So groundwater's moving through here really, really quite quickly. So in any event, when we got started, we planned for a pretty close well spacing, assuming a low hydraulic connectivity. Turned out we didn't need to use that close well spacing, but well, we had already put the wells in, so that's what we're going to do. The other thing is this was a pilot test, sort of proof of concept funded by ESTCP. And one of the big questions was we wanted to find out how long this barrier would last before we had to re-inject. Well, we had funding to monitor for 24 months. So we designed the injection based on our theoretical calculations that we'd run out of substrate after about 18 months. Well, why do you want it to? Well, if the project's only going to run 2 years, it's got to run out before the project is over. So we went out, we did that. Here are the guys out in the field. We don't do this anymore, but at the time, we mixed our substrate up in these little kiddie pools that we purchased at the local, I don't know where we got the kiddie pools, but, and you can see there, that's the white emulsion. Comes in drums, they pumped it in here, they dilute it with water, and then they ran it. You can see some hoses they run out. We typically use, we like to inject multiple wells at one time, and so hose comes out of this, goes through a distribution manifold. Each of the lines of the manifold has a pressure gauge, a flow meter, and a control valve, so we can make sure that each well gets the right amount of material. This is just another, actually I think there's a different site, but that set up the flow meter and the pressure gauges are at the wellhead. Okay, so here's a computer simulation of the oil injection process. Same model I showed you before. Now this assumes a homogeneous aquifer, so all the circle, everything looks nice and uniform. The way the injection process worked, as I described before, we injected every other well at one time. So we went out, we took, for each well, we injected 207 liters of diluted emulsion. That was 41 liters of EOS Pro and 166 liters of water. That got injected first, and then we followed that with another 625 liters of water per well. And that's intended to push the emulsion further out away from the well into the formation. But it also serves to clean out that well. If you don't inject the chase water, you leave oil close into the well, that oil is going to biodegrade over time. It's going to grow biomass. It's going to plug up your well. That may not really affect the performance initially, but if you need to come back in 3 years and re-inject, well, now you got a plugged up well that you have to clean out. So we really encourage people, inject a more concentrated solution first, and then chase water, push it out, clean out that well very well, and it'll significantly reduce your maintenance issues. Okay, as I said, now the pictures here you're seeing, on the left is the aqueous concentration, on the right is the sorbed concentration. At the end of the first day's injection, we've got little donuts of dissolved, well, not dissolved, aqueous phase oil around the wells we injected, none sort of in between, and the sorbed oil, again, we've got these sort of empty spots in between where we don't have good treatment. The next day, we came back out, we injected the other wells to complete the barrier. And then a month later, at least the computer model says, essentially 100% of the aqueous phase oil is now sorbed. And we have this nice sorbed oil treated zone. It's The center of the oil treated zone is drifted down gradient of the barrier a little bit. Because the oil, while it absorbs fairly quickly, it's not instantaneous. And so it does take a few days for it to migrate and absorb. But we would think this was a very nice uniform oil treated zone. We're going to get really good contact here and really good treatment. Overall, this whole process between installing the injection wells, mixing up the oil, 2 people did the injection in 2 days. They finished by Thursday and they packed up and went home. Okay, let's show some monitoring results. As I indicated, this project was designed to last 1.5 years. Graph on the right is, well, the top one is total fatty acids, organic carbon, and inorganic carbon. Prior to the injection, there was basically everything was below detection at day 0. You see immediate spike in fatty acids and TOC. It comes down fairly quickly. And then fatty acids, at least in the injection wells, fatty acids and TOC were constant for, well, out here to 800 days or so. So pretty good longevity. It does look like we started to sort of run out of gas here at the end. So what, about 2.5 years in the project, we're starting to run out of organic carbon. Further down gradient, I guess that's pink and black dots, concentrations are a little bit lower. But again, we're maintaining reasonably good carbon levels and fatty acid levels out there for several years after injection. One comment here, you see this kind of spike in inorganic carbon here at 800 days. They shut down the pump and treat system for a period here, and that's when we got this spike in inorganic carbon. That's because while carbon's still being released, it's also biodegrading. So we've got more biodegradation, more inorganic carbon production at that moment because we had more contact time. Okay, some other geochemistry. Dissolved iron throughout was essentially 0 initially. Big spike in dissolved iron immediately after injection, and then it kind of evens out. Takes a little while longer for the down gradient wells to have dissolved iron, but it goes up eventually. Methane, kind of similar pattern, very little methane initially, and then it gradually increases over the course of the project. Perchlorate, ClO4, this is basically a component of solid rocket fuel. You can see here initial perchlorate concentrations in all the wells were around 10 to the 4th micrograms per liter, or 10 milligrams per liter. Upgrading the barrier, concentrations remain essentially constant throughout the 2.5 year monitoring period. I've got data shown here. In the injection well, perchlorate dropped essentially instantly. I said they finished up injection on a Thursday. They went home for the weekend. They came back Monday, or I don't know what they sampled Monday or Tuesday, but the immediate following weekend, they did their first sampling after injection. Perchlorate was already below detection in the injection wells. It wasn't yet below detection in the first down gradient well. That took like another month. And then a few months later, perchlorate was detected in the 6-meter wells down gradient. Very, very good removal, and basically kept these numbers below detection limit for 2.5, 3 years. So 99.9 some percent removal. We were very, very happy about this. For TCA, I've got data showed for the injection well, 12 feet down gradient, and then 20 feet down gradient. That would be our I guess that's our 6-meter, yeah, roughly 6-meter wells. Again, prior to injection, TCA concentrations were about 10,000 micrograms per liter. Immediately after injection, TCA concentrations go down. We get a spike in dichloroethane and then chloroethane, and then they stabilize. Takes a little longer for this to occur further down gradient, but we see the same basic pattern where TCA concentrations are initially high, they drop down and stay low for 2.5, 3 years. Now, one thing I will say, we did not get 100% removal. While we got very good removal of TCA, we made DCA and chloroethane, and they did not completely degrade. The reason for that is, I think I mentioned, groundwater velocity in this zone was really pretty fast. So these contaminants were being rapidly flushed through that oil-treated zone. Contact time in the oil-treated zone, we figured, was about 1 week long. And that's simply, 1 week is not long enough to get 100% removal of the perchlorate. And I didn't show you, but we got essentially 100% removal of nitrate and the sulfate. Sulfate wasn't 100, but good removal of sulfate. And then also removal of this. It takes a while for the bacteria to chew through all those contaminants. So 1 week is too short. We've done some column tests. We tend to like 1 to 2 month contact time is usually what's good to get really good removal. If you have, particularly high contaminant concentrations, a lot of sulfates, some other things, you might want a little longer contact time than that even. One of the issues that was raised early on is, people were worried about, well, we're going to plug up the formation and we're not really going to get treatment down, the water isn't going to flow through it. So about 6 months after we installed the barrier, we went out with a geoprobe and we essentially tried to map the perchlorate distribution in the aquifer. The little, I guess, pink or purple dots here are all our geoprobe sampling points. As you can see here, in the blue points are actually our injection wells, and we have this zone here where perchlorate is below detection limit in all the points. Now, to the right, it's not impacted, but our edge of our barrier is right about here. So we got very good distribution here. Looks like there maybe was a little bit of flow around here on this side because we didn't get a good distribution. So the treatment, but there's really no evidence of significant flow bypassing. I would say in the future, you should probably plan on, if you need to, 100-foot wide treated zone or 100-meter wide treated zone, you might want to extend the barrier out 5 or 10 meters on the right, 5 or 10 meters on the left, just to have a little factor of safety on that edge. As I indicated again, flow bypassing was a real major concern. And so what we did is, prior to injection, we upgraded the barrier and we injected a pulse of bromide in a single well 2 meters up gradient. And then we sampled the injection wells. This is on day 1, there was no bromide in any injection well, or day -1, there was no bromide. 1 day after injection, we had this big pulse of bromide, essentially directly downgrading the injection well, and a few meters to the left and a few meters to the right. But then 34 days later, the bromide was all gone. So it just uniformly flushed the barrier. We went back 9 months later, did the same test. You get the same thing here, prior injection, there's no bromide. 2 days after injection, there's a big pulse of bromide right, essentially directly downgraded the injection point. Spreads a little to the left and a little to the right. And then 34 days later, it's to a large extent flushed through. I mean, it's a little bit slower here. Maybe we had a little bit of permeability loss here. So it spread out a little bit, but in the end, it's really was a non-event. We got very good treatment with no evidence of bypassing. Okay, Now, I've emphasized we want to get good contact efficiency. That's very, very important. I've also emphasized the way you get good contact efficiency is you inject more water and more oil, which costs more money, and nobody wants to do that. So with funding from ESTCP, we developed a design tool to sort of optimize this process. What I've got shown here is just a screenshot of the opening thing. Those are all buttons you can push on to. And so what you'll do to use the design tool, you enter the aquifer characteristics, the contaminants, the geochemistry. Then you enter some design information, you know, how wide the barrier is, what contact time you want, design life. And you specify the contact efficiency, or actually you specify the amount of oil and water you want to inject, and it calculates the contact efficiency based on those curves I showed you before. And it also prints out a cost estimate. Now, I'm not saying this is a final cost estimate, but at least it gives you an idea of the relative capital and life cycle costs. So here's an example. This is actually, well, the site conditions are the same as the pilot test I just showed you. However, this isn't for, that first barrier was only 15 meters wide. This is assuming the barrier is 30 meters wide, just to be a little more representative. Hydraulic connectivity, water thickness, maximum oil retention was measured in column tests. And we designed this for an 85% contact efficiency. And this graph shows the sort of relative distribution of costs versus well spacing. What you see here is if you use a really close well spacing of 5 feet, your total costs are really quite high. Total cost for this 30-meter barrier for design and installation would be about $225,000. If we increase the well spacing to, well, that looks like about 12.5 feet. Now we've reduced the total project cost down to closer to 100,000. That's because the drilling cost has come down quite a bit, but it hasn't really increased any of the other costs. Now, as we go to larger and larger well spacings, say you put a 15 or even a 30-foot well spacing, drilling costs go way down. You're not putting many wells in, but the labor costs increase significantly. We have many fewer wells to inject the same amount of water. It's going to take more time. Some people tend to think that the wider well spacing, the better, that saves money. Actually, there's really an optimum here. At this site, 10 to 20 feet well spacing seems to be the optimum. Probably not, this model certainly isn't accurate enough to distinguish between this point and this point, but this suggests that that's a pretty good spacing. And that wouldn't be unusual for other sites. We often find people going for, say, a 5-meter well spacing is fairly fairly common. Okay, tell you what, let's take a break here again and try to answer some questions, and maybe just let me catch a breath here for a second. Let me go back here. Chat, okay. Oh, okay, so I have a question. Do you change your strategy if you know you have high calcium, etc.? Well, okay, so if we knew, so a question, I mentioned that if you have high calcium, you're gonna have higher oil retention. Right now, the only answer I have for you if you have high calcium is quite simply you have to inject more oil. If you do, and again, more oil, more emulsified vegetable oil. If you have a higher oil retention, you need to inject more oil to get that good distribution. I am working on a treatment that hopefully we can reduce or solve that problem, but I haven't proven it works yet, so I can't really tell you any more about it. Hopefully a year from now I'll be able to say I've got that problem solved. Okay, got another question. What about application in rock? You're aware of a design tool also based on fracture distribution. No, I'm sorry to say, EVO or our EOS Pro and other things, done a number of projects in fractured rock. It works very, very well. We actually have some of our best results in fractured rock. Good treatment, but I will say I've never figured out a way that we could, in theory, apply the design tool to fractured rock, but I would need to know the oil retention of the fractures. And I don't have any good way to, well, do a column test on a fracture and figure that out. So the only thing we've figured out to do with fractured rock is we'll do little mini push-pull tests ahead of time to measure the oil retention in the fracture, and that'll tell you how much oil we need to inject. Any other questions? Well, I don't see anything here. If it's okay with everybody, and well, if it's not okay, I'm going to do it. I'm going to take a little break for maybe 2 or 3 minutes. What time is it now?
12:29.
It's 12:29. Let's come back at say 12:32, 12:33, and I can repeat. I need to get a drink of water, and maybe you can all go take a bio break, and we'll be back then. Thanks so much.
See you later.
Hello, everyone. Welcome back. I'm getting tired of talking. Somebody else needs to take over. Well, it's not too long. I'll try to wrap this up by 5 so you can all go off. No, I guess it's 7 o'clock your time. I'll try to wrap that up. Okay, so that's enough about the design tool. Let's see. So we did a project a few years back for ESTCP where we'd already done a number of these EVO projects. And what we noticed is that some of the projects worked very, very well, but there were a few projects that, well, we didn't get quite the results we wanted. And essentially the results of that task, that work, were this conceptual model that I've been sharing with you, where PCE and TC conversion to DC occurs very rapidly. It's honestly pretty easy with this technology. Tend to get very good removal. Conversion of DCE to vinyl chloride to ethene is just slower. Now, at the sites we looked at, this was not DCE stalled. At many of these sites, we had the helicocoides. We were producing ethene. It was just simply TCE was degrading faster than DC degraded. So it sort of appeared like DC was, well, DC was building up, and it gave that appearance. And so our early conclusion was not so much it wasn't happening, but we need to figure out a way to increase the DC degradation rate. And if we could do that, we could get a shorter cleanup time and we could save money. I've already talked to you about the causes of that. Well, realistically, probably the most common cause, or at least a very common cause, is simply if PC and TC are present, we're not going to get good conversion. The bacteria simply like PCE and TC better. They get more energy, they go faster, and the helicocoides is not going to effectively compete with them. So the limited substrate is going to be used. But once the PC and TC are gone, or at least they've been reduced to pretty low levels, then you should be able to start seeing pretty good DC conversion. Need adequate helicocoides numbers. As we said, bioaugment. You need nutrients, well, add them. We spent a lot of the previous presentation talking about improving oil distribution, bring hydrogen in direct contact with the DCE. For the last item I mentioned, low pH. That's really what I'm going to spend the rest of this talk on discussing. Low pH, really the solution is if you have a low pH, you have to raise it. The way you raise it is you add an alkali or a buffer that adds hydroxide and removes hydrogen protons. So let me get started on that. Most of this talk is really wrapped around the design tool we developed a few years ago, again for ESTCP. It's a different project. Again, it's essentially an Excel spreadsheet. You put in the site characteristics and aquifer description. You describe the treatment zone width and length, pore volumes, tell the model some about the geochemistry of the site, the target pH, background contaminant concentrations, and the substrate you add. And based on that, it calculates, well, one, the amount of base you need to maintain a neutral pH, and compares that to the amount you add. Well, this first project, this actually project was well before we had this tool. And this was a post-audit. Turns out we only added 3% of the base we needed. Well, not surprisingly, it didn't work out as well as we wanted. So this tool is available for download at www.Remediation. It's also available for download on the Barrio Wiki website. I'll show you more of that later. But first, what I want to do is rather than just plug the numbers in, I want to teach you some of essentially the theory behind this model. Okay. So you've seen this figure a bunch of times so far today, but this is just to reinforce that when you convert PCE to TCE, you release hydrochloric acid. When you convert TCE to DCE, you release hydrochloric acid. If you degrade a kilogram of PCE, you're going to make about 0.75 kilograms of hydrochloric acid. If you're only degrading micrograms per liter, that's not a big deal. But if you're trying to burn up DNAPL, you can produce a fair amount of HCl. That's going to lower the pH. You need to add a base to counteract that. Another source of acidity is substrate fermentation. Whether it be lactate you're adding or soybean oil, all these materials ferment to acetate and hydrogen. Eventually that acetate is going to get consumed, producing carbon dioxide. Carbon dioxide plus water makes H2CO3. That's carbonic acid. The more carbonic acid you add, the more base you need to neutralize that carbonic acid. Okay, let's spend a little bit more time talking about that reaction. Okay, as I indicated, if you produce CO2, it's going to react with water, and it's going to make H2CO3, carbonic acid. Carbonic acid will dissociate, releasing a hydrogen and a bicarbonate ion, or at least at pH about 8 it will. This graph below shows the distribution of different species. At pH 4, carbonic acid is a weak acid and it doesn't dissociate, so it doesn't release any H pluses, and it's 100% carbonic acid. However, at pH 7 or 8, let's say 8, HCO3 is going to completely disassociate, and it's going to release 1 mole of H plus for every mole of bicarbonic acid you add. So the amount of H plus you release depends upon the pH. At pH 8, you release 1 mole. At pH 4, you release 0 moles. Well, the way we figured out how to solve this in the model is we use this alpha function. This is a graph of alpha on the right. At pH 4, alpha is 1. At pH 8, alpha is almost 0. So this is the actual reaction in the model. So for every mole of CO2 you produce alpha carbonic acids and 1 minus alpha H pluses. So another way to say that, at pH 4, you produce 1 mole of H2CO3 and 0 moles of H plus protons, versus at pH 8. For a more reasonable pH, say pH 6.5, looks like maybe for every mole of CO2, you're going to produce, alpha is going to be 0.4, so you're going to produce 0.6 moles of H plus. Okay, that's carbonic acid production. That's another big source of acidity that's going to have to be neutralized. We take all those reactions, we add them together in the spreadsheet. For every mole of PCE converted to TCE, you're producing 1 mole of H pluses. Depending on these different organic substrates, you produce different amounts of carbonic acid. And depending on the type of electron acceptors, background electron acceptors, if you have a lot of dissolved iron, as the iron gets reduced, you actually consume protons and you release OHs. So iron reduction has sort of a buffering effect and will actually raise the pH. We take all these different processes into account and we sort of calculate out how much base you need to neutralize to have a good project. Okay, that's the amount of base produced. Now we have to think about the natural buffering capacity of the aquifer. Lots of people think about carbonates. A lot of aquifers actually have either large fragments or even just some shell fragments. There'll be calcium carbonate embedded in the aquifer. And we all know that if you take a little drop of calcium, if you have calcium carbonate, if you take your little HCl eyedropper and you drop it on it, it'll fizz. It'll release carbon dioxide. Well, that's not, it's actually a little more complicated than that. If you're at the land surface and you drop HCl on it, the calcium carbonate will dissolve. It will release CO2, and the CO2 will fizz. That only works completely at the land surface. If we're 10 meters below the water table, the CO2 can't fizz, it can't degas, and it just stays dissolved. And you get more of this reaction where you add HCO3, the calcium carbonate, and you make Ca+2 and 2 dissolved bicarbonates. Well, solubility of calcium carbonate is described by the solubility product. As we build up more dissolved calcium and more dissolved bicarbonate, the groundwater essentially becomes saturated with calcium carbonate. Since calcium carbonate is not very soluble, no more dissolves. If calcium carbonate doesn't dissolve, it doesn't neutralize acidity. So it turns out that at least below the water table, calcium carbonate's not really a very good buffer because it's just not that soluble. In contrast, a lot of the aquifers we work on will often have a fair amount of clays or iron oxides and aluminum oxides. That's the stuff that makes the soil look brown or reddish. Turns out iron oxides have a sort of unusual property that at low pH, so sort of let's say neutral pH, that iron oxide will absorb some hydroxides, OH minuses, and will also absorb some H pluses. And typically at sort of medium neutral pH, the amount of OH minuses and H pluses will be about balanced. At lower pH, it absorbs protons, it absorbs H pluses, and it can get loaded up with them. And so you've got this big reservoir of absorbed acidity. Versus at high pH, you remove all those protons and you actually absorb some OHs. So at a high pH, you have a large reservoir of absorbed alkalinity. So the solid phase surface actually generates a large buffering capacity. If you have a low pH, it wants to stay low. If you have a high pH, it wants to stay high. So once you get it where you want it, it's actually kind of a beneficial thing. But if you start out with a pH not where you want, well, you're gonna have to adjust it to bring it into action. The procedure we use is called aquifer buffering capacity, PHBC. The procedure is pretty simple. You take some soil, dry it, mix it with a calcium fluoride salt solution, 0.005 molar. And then we would take that solution and we would add varying amounts of sodium hydroxide to it. And as you add more sodium hydroxide, then we mix and let it equilibrate overnight. And then we'll measure the pH. And the figure on the right shows graphs of pH versus the amount of added hydroxide. And you can see there's, I don't know how many points of 1, 2, 3, 4, looks like 8 different depths. We collected samples at this one site. And what you see is the lines don't all lay on top of each other, but they all are fairly straight lines between, say, pH 4 and 7. And the slopes of the lines are all pretty constant. Well, the slope of that line is essentially the buffering capacity, or actually technically the inverse of the slope. So the aquifer buffering capacity is the mill equivalence of OH sorbed per change in pH. And we've done that at a bunch of sites, and it turns out that, well, this buffering capacity is, well, fairly easy to measure, and it really doesn't vary that much, at least within a site. You can see the slopes of all of these lines are about the same. So once you measure the buffering capacity, the other thing you need to worry about is just the initial pH of the site. I couldn't find a map of groundwater pH for Europe, but I did find one for soil. Our experience is that when you have acidic soil, you often have acidic groundwater. You can see in the upper part of this map, the dark greens or sort of medium greens. Dark green is a pH less than 4.5. Sort of medium green is between 4.5 and 5.5. These are, we would all consider fairly acidic and not suitable for reductive dechlorination. You're going to have to raise the pH of those. Farther south or in more arid areas, you see much higher soil pHs. Not saying you'll never, you know, if it's a big DNAPL site, you may still have a pH issue, but in general, in these more where the soils tend to be more alkaline, it's often turns out that aquifer buffering capacity is, well, low pH is less of an issue. Okay, so how are we going to raise the pH? The procedure we use, well, ever use is, if you're going to raise the pH, you need to add an alkali. There's a lot of theoretical possibilities, but in practice, people tend to use either carbonates, like sodium bicarbonate or sodium carbonate soda ash, hydroxides, either a sodium or a potassium hydroxide, caustic soda, caustic potash. These are quite soluble, so they're easy to use, but they generate a very high pH. If you inject, okay, so let me do that a little bit more. So easiest thing to use is something like a bicarbonate. Nice thing about it, it's reasonably soluble, and it generates the equilibrium pH is 8.3, which is very nice. Challenge is, it's got a maximum solubility of 7 to 8 grams per liter. But the bigger issue is here, if you look at it, it's this alpha term. If you want to raise the pH, well, I'll talk about alpha in a minute and explain that problem. But it turns out you just, for a lot of these carbonates, you sort of don't get that much bang for the buck. You don't get that many hydroxides released. And so you need a lot of it. Sodium hydroxide, potassium hydroxide, you get more bang for the buck. They have quite high aqueous solubility, so you can really adjust the pH very effectively with these. Problem is, if you make a solution of caustic soda and you inject it, it's got a very high pH. It may make the pH of your aquifer too high and you fry all the bugs. The other issue with these things is they're soluble. Soluble means they're easy to inject, but if you inject these materials in a biobarrier, they're going to float away over time and your pH is going to return to background. We use a lot of, like to use divalent hydroxides like calcium hydroxide and magnesium hydroxide. The advantage of these, they're much less soluble. Magnesium hydroxide in particular is essentially, you know, it's got a very, very low aqueous solubility. It's got a relatively low molecular weight and releases a lot of OH per mole. So actually you get a lot of bang per kilogram. You release a lot of OH per kilogram of material. The pH is higher than we'd like, but it's not really, really horrible. Turns out that actually it rarely ever gets up that high. And so I'm going to spend a fair minute today talking about using milk of magnesia or magnesium hydroxide and some of the challenges of that. So let me go back to the question about, I talked about CO2. Well, adding sodium bicarbonate is sort of the same. So if we have an acidic groundwater that's got extra protons in it, H pluses, and we add sodium bicarbonate to it, if it's an open system like the land surface, what happens is that disassociates, it makes H2CO3, carbonic acid. The carbonic acid separates back out into water and CO2, and the CO2 degasses. So in an open system at the land surface, bicarbonate works great because when you add it, you make CO2, the CO2 fizzes and it comes off. And in a way, you're almost air stripping out acid. So bicarbonate works great. Below the water table, it's more complicated. Again, now you take that sodium bicarbonate, but the reaction doesn't go all the way. And so for every mole of bicarbonate, you're going to produce alpha moles of carbonic acid and 1 minus moles of HCO3. And you're going to consume alpha moles of H plus. So at pH 7, alpha 0.18 maybe. So at pH 7, for every mole of sodium bicarbonate you add, you only consume 0.18 moles of acidity. Not very efficient. Can work, but not terribly efficient. Versus at pH 5, alpha is like, I don't know, 0.95. pH bicarbonate works great. Challenge is, I don't want the pH to be 5. I want it to be at least 6, and I'd really like it to be 7. That's what led us to work on using magnesium hydroxide. Here's, again, some column tests. This is the kind of thing we like. We take a column, we pack it in soil, we make our suspension, and we pump it through the column. These columns are relatively fine sand, but pretty high permeability, about 100 feet per day, hydraulic conductivity. Or if you want in centimeters per second, the initial hydraulic conductivity was 0.02, 0.03 centimeters per second. When we took plain magnesium hydroxide, now this was a very fine grained material. It had a particle size of about 1 micron. And this is a experimental result from the first test. So we pumped 3 pore volumes of plain water. Then we pumped 3 pore volumes of magnesium hydroxide suspension through it. And we monitored, and then we turned that off. We monitored the effluent. Magnesium hydroxide didn't break through at all initially, and then it broke through a little bit, maybe reached a maximum, maybe 24% breakthrough. And then when we stopped injecting, it rapidly went back down. So what we saw is this amount of alkalinity that showed in the effluent was 14% of what we injected. So 86% of the magnesium hydroxide got retained in this first, I think it was like 15, maybe 20, 30 centimeter long column. So really high retention. Plain magnesium hydroxide does not transport. Well, we spent a long time. We tried a whole bunch of different things. Eventually, we came to what I'm going to call treatment C here. Basically, it was some chemical reagents we could use to alter the surface charge of the magnesium hydroxide particles. When we did that, we were able to get much, much better transport. Same thing as before. We inject now the suspension. Magnesium hydroxide and effluent rises up very rapidly. We reach almost 100% of breakthrough. And then when we shut it off, yeah, the magnesium hydroxide goes down, but there's a little lag. And when we look at it compared to only 14% transport before, now we have 82% transport. Much better transport, much better distribution. And no permeability loss. In the early test, when we used plain mag hydroxide, you can see here the initial permeability was here. It dropped during the course of the test and stayed low. When we used treated magnesium hydroxide, actually it stays constant. Even seemed to increase a little bit, but I'm not sure if that was really significant, but really no apparent loss of permeability. So we were very, very happy about that. Okay, so let me show you some real results. This was a field pilot test. Actually a pretty large pilot test, but a pilot test conducted by Aptum in 2013. They put in a barrier, 20 injection points. They injected EOS, LS, and COBUF, injected some water, and then they monitored. Graph on the right is pH versus distance ground radiated to biobarrier. The aquifer pH prior to injection was fairly uniformly 4.5. Immediately, well, that was before injection. 45 days later, in the actual, right in the barrier, the pH was quite high. I think that was an injection well. So I said, magnesium hydroxide's supposed to have a pH of about 10.5. In actual fact, you never really see that high. So in this well, it was 8, and then it dropped lower at 100 days after injection. pH in that injection well had dropped. And we actually have a quite nice zone here, 25, and I guess about 10 meters wide, where we've increased the pH up to a very nice range for reductive decoordination. This was actually, they were treating explosives here, but good pH adjustment, and it lasted quite a long time. So they were very, very happy, and I think they have since gone full scale, but I'm not sure. Okay, as just to show you some of the output you can get from the design tool, what I did is I went to an example site. This was a site in Florida. pH was naturally low. I think the initial pH in aquifer was like 5.2 or something. It was a 130 meter long PRB. They added 20,000 pounds of oil, but only 240 pounds of magnesium hydroxide. It basically had no effect. Or, you know, maybe a tenth of the pH. You know, we didn't add nearly enough. Well, this was done well before I ever developed this design tool. So we went back and we tried to figure that out. So here's an analysis of how much base or how much alkali you would need to add to reach different target pHs down gradient aquifer. Now remember, the amount of base, particularly bicarbonates, you have to add varies as a function of pH. So, as I said, we injected 240 pounds. Based on the theory, at least, if we added 240 pounds of magnesium hydroxide, we'd raise the pH from maybe 5.2 to 5.3. Well, that's about what happened in the field. To get up to pH 7, you would need to add something over 10,000 pounds of magnesium hydroxide. You need to add, well, okay, so 12,000 pounds of magnesium hydroxide, 17,000 pounds of sodium hydroxide, 38,000 pounds of sodium carbonate, or, well, 200,000 pounds of bicarbonate. That's just not practical. So you see here that the target pH you're aiming for can have a dramatic influence in the amount of base you need to add to get to that pH value. Typically, you know, I want a pH of at least 6.5. I said our sort of magic number. look like based on dechlorination kinetics. Once you drop below 6.3, you're going to start inhibiting. Well, I'm not that good at aiming, so if I need to be at 6.3, I really want it to be 6.5 or 6.6 or 6.7. I tend to have a target pH somewhere between 6.5 and 7. And then if I underestimate or I don't do something perfect, I still have a little buffer there. But you can see here, you know, in some of these aquifers, they have such a strong buffering capacity that you need significant amounts, depending on the target pH. Well, if you're using magnesium hydroxide, it's less than the amount of oil you added, but it's comparable. It's and the bad news, you know, it's a significant cost. It's a significant part of the project if you have a low pH, and you just need to kind of plan for it. It's dealable, but it's not trivial. Okay, one last thing, I want to do a case study, show you a site. This was actually a pretty challenging site that we've been working on for the past few years. Initially, when we started out, this is a pretty sandy aquifer with a little bit of gravel, but it's overlain by a sandy clay. So it's essentially a confined aquifer. Waste solvents had been discharged into, well, they were stored in a building here, and it appears some were spilled on the ground, or maybe they migrated in the sewer, but they appeared to, some of the solvents have migrated down the sewer towards this little creek here. Well, when we got started, we were aware of this area. It wasn't until later on that we discovered that we were a real big hotspot over here at MW18 that I'll talk about in a minute. The aquifer naturally has a fairly low pH, probably about 5.5. But a complicating factor is we actually had a sulfuric acid plume that was migrating onto the property from the northeast. So this well over here, MW18, has a very, very low pH. The design consisted of, oh, I don't remember. Well, you can see a bunch of injection wells. I think probably a total of 60 injection points in the first phase. The wells were put 10 meters on center. Now, the way we did this is we had a single borehole, and we had 2 screens in the borehole, an upper and a lower screen. That way we could control the distribution of material. At MW2, initial contaminant concentration, there was a mixture of PCE and TCE, about 7,000 micrograms per liter at MW2, whereas MW4 is about 4,000 micrograms per liter. Like I said, pH of 4.5 to 5.5. 2 had actually a low sulfate level. We think that might have been due to some other hydrocarbon contaminant that might have been spilled here that consumed a bunch of the sulfate, versus over here at 16 further away at about 600 milligrams per liter sulfate. This is sort of what we planned on when we started the project. We were not aware until we actually had installed all the injection wells. MW18 was actually going to be a monitoring point to make sure we didn't push anything where it wasn't supposed to go. Once we put it in, though, we found very, very high concentrations. 150 milligrams per liter PCE and TCE, 30 of TCA, 30 of 1,1 DCE, very low pH, 3.6, and 2,000 milligrams per liter sulfate. Really, really nasty well. And as you'll see, it's taken us a while to get this one going. But okay, so first of all, I'm gonna really focus on MW2 and MW16 in this area. So we injected in 2013. This is a graph of MW2. It's an area graph showing everything's in micromolars. So 1 mole of PCE should make 1 mole of TCE, which should make 1 mole of DCE. You can see here it started out principally as PCE with a little bit of TCE and 1 DCE. We injected, those concentrations dropped rapidly. We made a bunch of cis DCE. And, you know, still a little bit of 1 DCE. But it really kind of stalled there. That was that pH stall I was talking about. If you look up here, initially the pH here was about 5.5. Gradually we increased it up almost 6.5. And we started to make a little methane. I like to use what's called sum of organic chlorine and chlorine numbers. Sum of organic chlorine here started out at about 200 micromolar, dropped a little bit when we converted all that PCE to DCE, but it kind of stalled there, or at least it slowed down. The chlorine number here is 2. That means that for every mole of ethene, there's 2 chlorines. Well, that's DCE. So we're kind of stuck here at DCE, not a lot of happening. Well, we honestly didn't really know what was going on. We tried a bunch of things. It wasn't really pH, as you can see. I mean, the pH isn't perfect, but it's increasing. It's getting better. Well, I mentioned before that, well, we didn't always add nitrogen and phosphorus. Turned out when this project got started, we didn't add nitrogen and phosphorus. So we didn't add B12 because, I don't know, because we're dumb. We didn't add it. Well, it turned out that this was one of those sites I mentioned that B12 can be limiting in high sulfate. Well, we did some lab tests. We collected groundwater. We did some microcosms. Did a pilot test, and it turned out when we added extra nitrogen, phosphorus, and B12, it worked great. So we went back out in the field. We re-injected this area with B12, more phosphorus, more B12. Got great results. Bam! Cis DC is coming down, burned through most of the material. Some organic chlorine is going down. Chlorine numbers going down, and down here at the end of the project, basically the only thing left here. I mean, I'm not saying that we might have 1 or 2 micrograms per liter of vinyl chloride, but it's basically all converted, and great result. Similar to MW16, sort of similar results, but if I remember, MW2 started out at about 50 micromolar and then went down. MW16 actually started about 25 micromolar. And immediately after injection, it jumped up. Well, what we think happened was when we stimulated that PCE to TC to DC conversion, DC is more soluble, it desorbed. So we got a big little pulse of DC coming out, but it went down. And then it kind of stabilized. We added more nutrients, and again, this has gone down. This site's not gone quite as far, but we're pretty well on our way. So again, we're really pretty happy. We were able to get pretty much complete conversion, and we're thinking it's working. We may have to come back and re-inject soon, but overall, this area's worked. MW18 was much, much more challenging. As I indicated, we had like 200 milligrams per liter chlorinated solvents. When you get that high a concentration, the solvent itself can be toxic to the organism. So this was just, we weren't really intending to treat this area initially. It was right sort of on the edge. So we, nearby, we injected in 13, but we really did nothing other than maybe burn up a little sulfate. We came back to this area in 2018. We put in some new injection wells. We doubled the amount of EOS Pro we injected. We injected extra nitrogen, extra phosphorus, extra B12, extra yeast extract. And just, I have to tell you, it was a massive amount of potassium bicarbonate and magnesium hydroxide. But we're actually pretty happy with the results. You can see here, we injected in 18. Pretty much immediately after injection, the pH jumped way up. So we're now at a pH of around 6.5. So we went from 3.5 to 6.5. Sulfate has dropped dramatically. It took a little while to burn through it all. Immediately after injection, we get a sharp drop. If you look here, we really haven't produced much cis yet, but we've got big drops in PCE. Well, what we think actually happened here is that we just absorbed the PCE to all that oil we just injected. But then a little while later, you know, now the bugs wake up, they start chewing on it. We make a fair amount of DCE. Now, at this point in time, pretty much all the PCE is gone, but we still have a little TCE. Remember, we had an enormous amount. It may take a while to burn through all that PCE before we're actually going to get good treatment. And we're going to be able to burn through the rest of the DCE. I also said we had TCA here. Basically, it turns out PC and TC inhibit TCA degradation, and TCA inhibits PC degradation. So they're sort of co-inhibitors. This was a very challenging site, but it does turn out, you know, it looks like we basically sorbed a bunch of TCA. Now, long-term, that's not good. Short-term, that's actually a pretty good thing. Since TCA inhibits DCE degradation, since we sorbed it, it's less inhibitory, and we can work on chewing through these. Once we get this cleaned up, we're pretty confident we can burn through these. And you can see that in the chlorinated numbers, where originally it was high, now we're about 2. Doesn't look like much, but we're gradually burning through that DCE, and we think within a, now, you know, warning, it's going to take a few years. This was a really nasty well, but it seems like we're making some progress. So in summary, anaerobic bio works. It's pretty easy to use. In terms of emulsified oil, it does last fairly long, so it's lower maintenance. We feel like we very well understand the fluid mechanics of EVO transport and how to design the process. That said, burning up PCE and burning up TCE is pretty straightforward. You have to work harder. You can degrade DCE. We've shown it, but it definitely is a little more complicated. If bacteria are limited, we'll add bacteria. If nutrients are limited, add nutrients. If hydrogen are limited, you just have to work and make sure you get good contact. And, you know, finally, if the pH is too low, well, add alkali and raise the pH. So that's all I got. The last thing I have for you is we've been working for years on this project at Barrio Wiki. It's a website that has a lot of really good information on environmental remediation. Shown below are some of the articles on it. A number of the design tools I talked about, the emulsified vegetable oil design tool, the pH base addition design tool, they're all here. So please go check it out. And now time for questions. Okay, so let me go back here. Okay, so let me pick up some questions there. Okay, so. Okay, I got a question. If we wish to use sodium hydroxide as pH buffer, what are the best practices to avoid suffocation at EVO in live mixing, buffering, Barrio addition? Oh, it's okay. If you want to use sodium hydroxide, I can't, sorry, I can't come up with a sort of simple statement about how to use sodium hydroxide. I think there's a way to do with it, but you just have to carefully sort of manage the process to make sure that you never let the pH get too high. If the pH gets too high, you're just going to do weird things to geochemistry. So you'd have to carefully meter it in and just add enough to get the pH up to target level, but not too high. Robert Wagenfeld has answered, and I generally sort of agree with his statement that it, to Jason Tilson, I'll talk to you offline, but that's, we just never use sodium hydroxide just because it's just really challenging technically. No other questions?
I guess no, Robert, no other question from the chat. I can try also to, I don't know, if take another minute to
or can you open up speakers so they can talk? If it might actually work better.
Exactly, yes. Now the organizers give me the powerful button of host, so I can decide everything. I will unmute, allow participant to unmute themselves. So participant, now you may you may bring your voice to this course. Please intervene. Maybe Robert, break the ice.
Won't break the ice.
What's your favorite wine? Maybe I need to go back. Sorry, don't look at the screen while I'm going back. There we are. Okay, I got my glass of Chianti and all right. I guess no questions.
No.
Thank you so much.
No question. Thank you very much. If I may, I would like to share briefly my screen because yeah, I would like also to thank some of our sponsors that through them we were able to let's say to organize everything in here in Remtech Europe. Just a moment, then we will unmute all so that we may make also some final goodbye. Just a moment, let me share my screen. Okay. I would like to thank you all the guys here represented. If we were able to organize this event with 16 sessions, it was thanks to our sponsors. Now I will unmute all for a final goodbye. And no, an important thing, there are many experts also listening here. Also some people from the scientific committee like Paul. We will meet, the scientific committee will meet in February, and in March we will release the call for abstract for Remtech 2021. So stay in touch, because if you have something that is worth to be listened, like the training courses of this afternoon from Paul and from Bob, feel free to make any proposal. So yes, I will try to unmute all just a moment so that we can say a general hello to everybody. So let's make just a moment. I don't know how to do because you know, participants unmute all. Oh, so everybody is unmuted. You may let's say let's try to make a final goodbye.
Marco, if everybody starts their video, you can get a screenshot of everybody on the screen.
Okay, sorry, you are right. I have to stop sharing. The sponsors have already their minute of glory. So I try to start the video of everybody. Not easy for. Okay, Paul. Okay. So I will go for a general, let's say, a general picture of everybody. Okay. Please turn on your video when asked, so that we may see that you are really people. Okay. Please turn on. Okay, Paul. Thank you. Also the other, please.
You gotta get a group photo. Everybody stand in front of the stairs.
Yeah, exactly.
That's the idea. I'm not sure whether the participants can turn on their videos, though, can they?
No, I have the magical button of a chair, but I can do it just one per time. So time. Okay. Please turn on your video who is abled. And your microphone is already free for your comments. And also, if you have some comments about Remtech Europe, you may do it. We are here also for some feedback, if you like. Turn on your video again. I did everybody is able to turn on them.
Is this the last Remtech, Marco?
You're just 5 people. I'm sure that there are also other people. But Melanie, I know you by person. Turn on your video.
You've got 36 people still online, Marco, which is pretty incredible at this time of the Friday evening.
Yes, but I want to make a picture with my mobile phone, all the people, but they don't turn on the video. It's impossible.
They're doing their makeup.
I think there's a bunch of people out there in their pajamas.
Yes. Okay, Deborah,
Stefano, they have to prove it.
Aline, thank you. Turn on your video, come on. Stefano, by the way, is a great expert of Tuscany Environmental Protection Agency with a lot of projects on this field. Thank you, Stefano, for coming.
I guess people are shy.
Or maybe they're working at a desk without a camera. Some people don't have cameras.
I cannot make anything else because you can everybody could turn on their video, but they don't.
Oh, well.
So they say yes, we have to close and go dinner. I don't know what. Okay, so basically, thank you again, everybody. Thank you for all the attendance. I'm sure I will be also. We are going also by tomorrow to work to the next edition. I think Paul and Bob, it was a great couple of sessions this afternoon. I really appreciate, and I'm sure my idea is also to insist on formation at high level, like experienced professors from big university worldwide can give to the floor. And this is also a way where, let's say, those kind of courses can arrive also to the developing countries, for instance. So it's very useful to have prepared lawmakers, prepared new project managers, prepared new stakeholders, so in every part of the world. So Robert, Bob and Paul, thank you very much for being here. Thank you also for the real people that are now online, and I can say just see you next year. It will be NEREMTech 2021. We don't know if it will be completely online, hybrid or face-to-face. We don't know. Let's see the COVID-19 situation. But for this year, I'm very satisfied of all the session I did and we did together. And so that's it. See you next year. Bye-bye.
Thanks
Thank
so
you,
much.
everybody.
Bye-bye.
Arrivederci.
Ciao.
Arrivederci.
Ciao.
Bye-bye.